Welcome to the executive level overview of the Army Corps of Engineers Builder application. This short module will familiarize organizational decision makers with the purpose, capabilities, and advantages of using Builder to help manage your facility portfolio. This module is for executive level decision makers and individuals who review reports and other data generated by Builder. Let's start by discussing the problems faced by facility managers using traditional facility management techniques. Managing facilities by tracking deferred work is difficult. Deferred work, also known as deficiencies, is the legacy metric used in most facility management programs. Deferred work is detected through interviews and inspections, and the deficiencies reported are collected in a list that is then used to build a budget. With this method, the building's Facility Condition Index, or FCI, is correct for a single moment in time. In other words, that week or two when the inspections were accomplished. It's a single data point that becomes less useful to decision makers the further we get from that inspection date. We have no ability to forecast into the future with this method, other than by guessing. By using old data to guess at our future needs, we are actually trying to manage the future by looking at the past. Imagine driving down a curvy road. The road ahead represents the future, and the curves represent the uncertainty of your facility's needs. Using the deficiency model to manage our facilities, the past, seen in the rearview mirror, is all we can see. The future is obscured. If the rearview mirror is the only tool available to the driver, it only takes one curve in the road ahead to cause an accident. And yet, every day, facility managers use deferred maintenance, or FCI, to guide future facility budget needs. Seems a little crazy, right? Seeing this, the Department of Defense sought out a new solution. In February of 2013, the Institute for Defense Analysis published a study of federal facility management practices and made recommendations for the future. They said that we really need a metric-based, data-driven system that is continually updated so data remains accurate and relevant. It should be forward-looking and risk-focused. This would allow anticipation of facility problems coming at us rather than just reaction to problems that have already arrived. Later that same year, in September 2013, the Office of the Undersecretary of Defense for Acquisition, Technology, and Logistics mandated that all of the Department of Defense, or DoD, will use the Sustainment Management System, or SMS, as the system of record for strategic facility planning. The memo, which you can read by clicking on the View Document button, gives reasons for the decision, such as standardizing the facility condition assessment process, ensuring reliable, consistent data, and giving more credibility to the DoD Asset Management Program. Since this solution is a federal asset, it is free of any licensing cost for government users. The Builder software is part of that Sustainment Management System suite mandated by that letter. This collection of systems has been developed by the U.S. Army Corps of Engineers Construction Engineering Research Laboratory, or CERL. They've been creating the data models, algorithms, and user interfaces since the 1970s. The SMS embodies Builder, Paver, Roofer, and Railer. Each of these systems is specialized for their focus areas: buildings, pavement, railways, and roofs. Builder, though, stands out as a purely strategic planning tool and not also a project execution tool. Builder is web-based, so it can be accessed from any internet-connected computer through its web browser. The data in Builder is stored in the cloud and is available immediately whenever an analyst needs it, but is highly secure against outside intrusion. The modern web service infrastructure enables our CMMS system to integrate with Builder. Keeping your new strategic planning tool connected to your existing project management system is critical. Builder data can be downloaded into offline, handheld tablets for easy field assessments away from internet connectivity. The Builder software breaks every building down into small pieces called sections. Examples of sections are, for instance, 3,000 square feet of exterior brick wall, one 30-ton chiller, 45 interior wood doors, or all exit lights on the 5th floor. Inventory details are captured for each section, enabling Builder to know expected life and replacement costs. When inspectors are in the field inspecting a building, they're inspecting individual sections. And when Builder determines that work is needed, the work items created are at the section level. In fact, almost all of the calculations in Builder happen at the section level. Builder already knows certain things about all sections in a building. This preloaded data comes from industry-recognized construction data providers. One of the most important things Builder knows is each section's expected lifespan, or more precisely, life cycle. This graph shows a generic section life cycle. Time is on the x-axis, and the section condition index is on the y. When the section is installed, it is brand new, and its CI is 100. As time passes, we move along the curve to the right. Notice how the condition remains high early in its life, but as it gets older still, deterioration accelerates more rapidly. When the CI reaches a score of 40, it is no longer reliable, and so Builder considers the section to be at failure. This section's expected service life, then, is 20 years. The Builder database contains curve data similar to this one for thousands of sections. Builder also knows the cost to repair or replace each section in a building. With this lifecycle chart, again depicting a generic section, we can discuss the cost of deferred maintenance and the proper timing of that maintenance to minimize the cost. The two dots on the curve show different investment decision points. The green dot, at a CI of 60, represents a time when Builder might recommend a repair to this section. The blue dot further down, at a CI of 20, is past the failure point. To repair the section at the blue dot would cost 4 to 5 times as much as it would have cost to repair it earlier, as Builder recommended. Notice also how the same amount of deterioration, 40%, occurred during the last 3 years as occurred during the first 17 years. The cost of deferred maintenance is high and measurable. This is one way Builder can help you optimize your investments by minimizing the costly penalty of missing timely work actions. Using the RS means lifecycle data and graphs to predict section condition works well, but it can't predict local conditions or events that are outside of the standard data model. Additional real-world data from the field is needed to make that curve reflect the condition of the building and sections even more accurately. The Builder condition inspection is performed by trained inspectors to assess the condition of a section at a single point in time. Think of it as a snapshot. The inspection updates the condition index. Using the life cycle graph again, we illustrate how inspections update the curve by modifying it to reflect real-world conditions. See how in 2005, the first inspection is performed on the section. At that point in time, the inspector's assessment matches the predicted condition index in Builder. In other words, the inspector's rating sits on the predicted condition curve. But in 2010, a second inspection is performed. This time the inspector rates the condition as less than the Builder predicted score. This is probably due to local conditions that are causing the section to deteriorate faster than normal. Notice what Builder does with this new data. It updates the CI with a new lower rating and adjusts the remainder of the life cycle curve to reflect the higher rate of deterioration. Now, rather than an expected total service life of 20 years originally predicted, this section has a shorter expected service life of only 17 years because of the on-the-ground data provided by the inspector. Okay, so we've talked a great deal about sections. It's time to show how they relate to the big picture. Sections collect and organize the assets inside a building. Taken all together, they reflect the building itself. But before we can show you how that happens, we need to present the organization of those sections within a building. Builder uses the Uniformat 2 system, which is an industry-standard method of organizing the parts of a building. The building is made up of many systems, such as roofing, HVAC, and interior finishes. Every system is comprised of components to further categorize the inventory. So the interior finish system has doors, carpeting, ceiling tiles, etc. And finally, under each component resides the many sections. So under the doors component, we might find bifold doors, wood doors, and metal doors. Here is where the real power of Builder starts to become evident. A building can be comprised of thousands of sections. What if we could see them all at once? Let's start with exterior walls. then windows. Next, let's add carpeting. You get the picture. Each curve represents a section, and they add up quickly. By overlaying the life cycle curves of each of those thousands of sections onto one graph, we can see the condition of the entire building in one glance. The only problem is the sheer quantity of data in front of us and the difficulty reading it in this form. This is where the roll-up becomes necessary. The Builder software takes all of this data from the sections and will roll up the condition scores. So Builder can provide an overall condition rating for a specific component or system, or most usefully, the entire building. This building level condition index is called the BCI. You can see by this graph how the BCI, indicated by the thicker red line, is calculated as an aggregate of the section condition indices. Here's another, less cluttered look at the building condition index curve. The curve and every point along it represent the condition of the building at any point in time. Notice how it is not smooth like the section curve. The bumps and bends in the BCI curve are due to the way the section CIs of the many sections in the building are faring. Each little bump represents a small increase due to a section or sections being repaired or replaced at that point in time. The large jump you see near the middle of the curve is due to a major renovation to the building, which repaired or replaced many sections at once. The BCI is a facility manager's metric for assessing the building's overall reliability. As the line gets lower on the scale, the reliability of the building as a whole decreases. But BCI alone does not provide the full picture of our building. Adding to that full picture is another of the high-level metrics in Builder, the functionality index. A building's FI score indicates its ability to serve its intended purpose. For example, how well does this new office building fulfill the role of division headquarters? The questions that lead to this score include configuration, energy usage, and compliance issues like ADA. Functionality is assessed at the building level only, so smaller parts of the building, such as sections, are not rated individually as they are with condition rating. Another difference from condition rating is that the FI does not degrade continually in the software. The FI changes only when there is a new functionality assessment. So it ends up looking like a step function, with each step representing a new assessment. Here is a functionality curve, if you will. Each time the line drops or rises, a functionality assessment has occurred. Notice that the major renovation to the building did improve the FI rating, but the improvement wasn't recorded until several years after the renovation was completed. The functionality improvement had to wait until the next assessment occurred to make it into Builder. The single building level metric that can be used to identify how well a facility performs is the Performance Index, or PI. Derived from combining the BCI and FI scores, the Performance Index gives planners and managers an idea of a building's overall ability to support the mission reliably. Now we're able to see this big picture of how our building is doing. So the commander now has a metric that can give her a level of confidence that the base hospital can meet the demands of the mission without failure. It's a rating of a building's overall performance, and the algorithm uses a combination of the BCI and the FI to calculate. Here you can see how the Building Condition Index and Functionality Index lines in gray are combined to create the Performance Index in orange. With a good understanding of the condition curves and indices, we can now move on to work creation in Builder. This is the process where Builder determines that a section's condition is below the standard set by the organization. In this case, we have a section of roofing. The standard that has been set for this section is a CI of 58. This means that the Builder user wants this section to be maintained at a condition index of 58. When the section falls to this level, Builder assigns that section to be repaired. Once that work is completed and the data is updated in Builder, a new curve is drawn for that section. You can see the gain in the condition index to a nearly new state, or a CI of 95. Then a new but steeper curve is drawn to the right. It's steeper because repaired items degrade faster than brand new ones. Service life was added to the section, extending its service life by about 10 years. In a traditional inspection, the assessor identifies work. In Builder, the assessor tells the organization the condition, and the organization can set what is good enough and what needs work with a uniform and systematic approach. We talked a moment ago about how the system creates work. This was a prelude to the work configuration process. Prior to creating the work plan, the system must learn the values of that organization. These organizational values are translated into Builder through the creation of standards, which are like condition index tripwires, policies that guide the application of the standards, priorities determine which work items are most important, and funding, how much money is available and how it may be used. The work configuration process is complicated, but as executive-level decision makers, it's important you understand generally how the process works so you'll know how and why your data was derived when it lands on your desk. Click play to start a short video.
Let's look at facility work planning. Work planning is the creation of work items in a building and the order in which that work should be completed. The traditional method, the one that's been around for years, is based on the deficiencies found by inspectors. Deficiencies are items which have been found to be in disrepair or are inoperative. The inspector finds items that are broken or are in some other way not good enough and records them as deficiencies. And then he or she estimates the cost to repair or replace them. That list of deficiencies becomes the work item list. It is entirely dependent on the perspective and experience of the individual inspectors. So there can be great variance in the results if multiple inspectors are used across your property portfolio. One of the most important results is the Facility Condition Index, or FCI. The FCI is the cost of required work, maintenance, repair, and replacement, divided by the present replacement value of the building. In this traditional model, required work is only the deficiencies that were seen and recorded by the inspectors. On the other hand, Builder uses an engineered, repeatable, transparent, and defendable approach to work planning. In Builder, the software looks at every single building component. Every building component is evaluated using a series of algorithms. We're going to represent these very complex processes here as a series of boxes. The first box is called the work generator. The Builder algorithms are guided by a set of rules that have been put in place by the Builder user. These rules begin with standards, which are specific condition values that act as triggers for generating work. They will be compared against the actual condition value of the components in the building. Policies are the rules for how the standards are to be applied to the different kinds of components. These rules will be applied to each component once the conveyor belt starts up. The output of this box will be components that do not meet organizational expectations for condition. The organization's policies establish the condition standard that each component must meet. Each of these components, which are now called work items, also have an associated cost for the repair or replacement work needed. Components that meet organizational expectations are not selected for work and move out of the process. You probably have thousands of components in your buildings, but Builder completes this process in just a few seconds. The next box in this series is prioritization. This set of algorithms will determine a prioritized order to arrange the work items, based on the importance placed on certain attributes of the components themselves. These rules, which are planned and selected by the organization, are called the prioritization scheme. The prioritization scheme embodies the fiscal, business, and mission-related principles your organization considers most important. For instance, your organization's leadership may consider avoiding the risk of building failure to be very important, or the maintenance of critical systems in your buildings may be a top priority, or the completion of work items with the highest return on investment may be a concern. These and other principles can be enforced in the prioritization scheme. Each work item is compared to the scheme to determine its priority score. The output for this process is an ordered list of work items ranked by priority. At this point, the system knows which components need work, how much that work costs, and in what order the work should be completed. These prioritized work items then move down the line to the final process, where Builder assigns funding to them. Your organization tells Builder how much money is available for each year and any restrictions on that funding. The prioritized work list moves into the last box, and funds are applied according to the amounts available from the organization. Top priority work items get funded first, and all monies are used to fund as many of the work items as possible. When the money runs out, the leftover lower priority items remain unfunded. In the end, two work item lists emerge from this box: the funded work items and the unfunded work items. In total, these two lists are what it's all about. Taken together, they represent the amount of work that your facility needs. These lists can then be used for project planning, fiscal planning, or long-range scenario development. Builder can also use the unfunded work to calculate the FCI. The cost of the unfunded work items becomes the numerator in the FCI equation. Of course, if this funding is not used for some reason, then Builder assumes that all the work items generated are unfunded. This FCI value is firmly based on the consistent application of your organization's business principles, making this FCI calculation even more significant. Now you can see what we mean when we say that Builder is an engineered, repeatable, transparent, and defendable process. Ultimately, Builder allows you to create a customized and concrete plan for spending your organization's limited money in the most efficient way possible.
Okay. In that animation, we briefly alluded to another feature of Builder, the Scenario Analysis tool. This tool is one of the most powerful features in Builder. It can project your facility metrics up to 10 years into the future. It repeats the annual work planning process, assuming for each new year that the recommended and funded work was completed and that any backlog was passed on to the next year. It also continues to degrade all sections, generating new work items each year as sections fall below standards. The result is insight into the long-term impact of decisions on condition, performance, and the estimated work backlog. The scenario tool lets the analyst evaluate multiple paths with differing variables. He might vary the budget slightly in one scenario to compare to another, seeing which is more effective at maintaining overall facility condition. He can also change aspects of the policies or the prioritization of work items. This simulation engine enables decision makers to build a more sound facility investment strategy. This graphic helps to demonstrate the repetitive, cyclical nature of the scenario tool, running complete work planning processes over and over up to 10 years into the future. The result of the previous year's process informs the next year, and so on. You may be familiar with the GIGO principle of garbage in, garbage out. As an engineered decision support toolset, accurate results rely on accurate data at the input. The sources of these data might be third-party assessors, on-staff facility managers, and technicians. It's important to implement a plan to update those categories of data over time. Again, integration with a project execution CMMS is valuable, as the majority of facility changes will be tracked in that system. Builder is designed for you, the executive-level decision maker. A real-time toolset that measures every facility using the same yardstick will help you make better-informed, strategic investment decisions. It can allow you to anticipate, rather than react to, major failures by identifying potential issues before they occur. And it can help feed your tactical-level work management systems with the most important, highest ROI work items. In the end, Builder gives you the right data at the right time, at the right level.